Alpha Centauri does not look frightening when you first hear its name. It sounds gentle, almost familiar, like a neighbor across the street, rather than a distant and alien star system. It sits only 4.37 light-years from Earth, closer than any other stellar system beyond our own. In the scale of the galaxy, that is almost nothing. If the Milky Way were the size of Earth, Alpha Centauri would be only a few meters away. That closeness is what made it so seductive to generations of scientists and dreamers. It became the first place humanity imagined reaching beyond the Sun. It was the target of our earliest interstellar probes on paper, the destination of countless science fiction journeys, the place where another Earth was supposed to be waiting. But Alpha Centauri is not one star. It is three. Two of them, Alpha Centauri A and Alpha Centauri B, are locked in a slow gravitational dance, circling each other over a period of about 8 decades. They are both similar to our Sun in size and temperature, which made them even more attractive to scientists searching for places where life might exist. A is slightly larger and brighter than the Sun, while B is slightly smaller and cooler. Together, they form a bright double star in the southern sky, visible even to the naked eye from Earth. The third member of the system is Proxima Centauri, a small red dwarf star that orbits far from the other two. It is dim, unstable, and easily overlooked, yet it is technically the closest star to Earth. Proxima Centauri is where much of the real drama of this system is unfolding. It hosts at least one known planet, Proxima b, a world roughly the mass of Earth that orbits inside the star's so-called habitable zone, where liquid water could in theory exist. For decades, this combination of proximity and potential made Alpha Centauri feel like a promise. If there was another living world nearby, surely it would be there. When astronomers discovered Proxima b in the year 2016, excitement rippled through the scientific community. Here was a rocky planet in the right temperature range, orbiting the nearest star to our own. It felt like destiny. It felt like the universe was inviting us to look closer. Yet even before James Webb was launched, cracks were already appearing in this optimistic picture. Red dwarf stars like Proxima Centauri are not calm, gentle suns. They are violent and unpredictable. They erupt with powerful flares that can bathe nearby planets in radiation. They blast out streams of charged particles that can strip atmospheres away, and Proxima b orbits extremely close to its star, much closer than Earth is to the Sun, making it especially vulnerable. Alpha Centauri A and B bring their own complications. Their gravitational pull on each other creates a dynamic and shifting environment. Any planets orbiting one of these stars must survive the constant tug of the other. Over millions of years, those forces can destabilize orbits, send worlds spiraling inward, or fling them into cold interstellar space. So even though Alpha Centauri is close, it is not simple. It is a laboratory of extremes, a place where stars interact in ways that our own quiet solar system never experiences. It is here that James Webb, not by directly staring into the blazing faces of Alpha Centauri A and B, but by studying the faint infrared signatures around them and around Proxima Centauri, has begun to reshape what we thought we knew. James Webb does not need to see oceans or continents to tell a story. It reads heat, dust, and light stretched into long invisible wavelengths. It can detect the warmth of debris disks, the glow of gas, the fingerprints of molecules. Around Alpha Centauri, it is helping scientists map the environments in which planets form and struggle to survive. What is emerging from those data is not a picture of a friendly neighbor, but of a system under constant stress. The closer we look at Alpha Centauri, the more it begins to resemble a warning rather than a refuge. These stars are not quietly nurturing worlds in stable orbits. They are pouring out energy, reshaping space around them, and creating conditions that challenge the very idea of habitability. The nearest stars in the universe may be some of the most hostile places we could ever try to visit. And that is what makes this story so unsettling. If even our closest neighbors are so dangerous, what does that say about the rest of the galaxy? Alpha Centauri has been observed for more than a century. Yet in many ways, we are only now beginning to understand how strange and intense it truly is. Earlier telescopes gave us light and motion, points of brightness drifting across the sky. James Webb brings something different. It brings the ability to sense heat and chemistry in the darkness between stars. It does not just tell us where things are, it tells us what they are made of. and how violently they are being shaped by their environment. Around Alpha Centauri A and B, there are faint disks of dust and debris. These are the leftovers of planet formation, tiny grains of rock and ice orbiting in wide belts. In a quiet system like our own, those belts can remain stable for billions of years. In a binary system like Alpha Centauri, they are constantly stirred and disturbed. Webb sees those disks glowing faintly in infrared light, warmed by the stars and by collisions between particles. Every collision releases energy. Every impact reshapes the disk. It is a sign of ongoing chaos, not calm stability. This matters because planets are born from those disks. If the disks are turbulent, the planets that emerge from them inherit that instability. Their orbits become more elliptical, more tilted, more likely to cross paths with other worlds. Over long spans of time, those interactions can lead to catastrophic impacts or to planets being thrown out of their systems entirely. A world does not need to be destroyed by a star to become uninhabitable. It can simply be pushed into a cold and empty orbit where life can never gain a foothold. Proxima Centauri adds another layer of danger. Red dwarf stars are small, but they are incredibly active. They rotate quickly, and their magnetic fields twist and snap like overstressed cables. When that happens, enormous flares erupt from the star's surface. These flares release bursts of ultraviolet and X-ray radiation that can be thousands of times more intense than anything Earth receives from the Sun. Proxima b orbits so close to Proxima Centauri that a year on that planet lasts only about 11 Earth days. It is locked deep inside the star's magnetic influence. When Proxima Centauri flares, Proxima b is hit almost directly. Webb and other observatories have helped scientists model how often these flares occur and how powerful they are. The answer is deeply troubling. Proxima Centauri produces major flares far more frequently than our Sun, sometimes multiple times in a single day. Each flare sends a storm of radiation and charged particles outward. If Proxima b has an atmosphere, those storms slam into it again and again. Over time, they can erode it, molecule by molecule, carrying away the very air that life would need to breathe. Even a thick atmosphere would struggle to survive under such constant assault. What makes this even more severe is the planet's likely tidal locking. Because Proxima b is so close to its star, gravity has probably forced it to always show the same face to Proxima Centauri. One side of the planet is in eternal daylight, blasted by radiation and heat. The other side is locked in endless night, freezing and dark. Between them lies a narrow band of twilight, where temperatures might be moderate. But even there, the sky would be filled with the flickering of flares and the invisible rain of high-energy particles. James Webb cannot see the surface of Proxima b directly, but it can measure the infrared glow of the system and look for the chemical signatures of gases that might indicate an atmosphere. So far, no clear signs of a thick, stable atmosphere have been confirmed. That does not mean none exists, but it does mean that if one is there, it is either thin, unusual, or constantly being replenished by volcanic activity or other processes. All of this forces a difficult realization. A planet can sit in the right temperature zone and still be utterly hostile to life. Heat alone does not make a world habitable. Stability matters. Protection matters. Without a strong magnetic field and a robust atmosphere, a planet is naked before its star. Alpha Centauri, once seen as our most welcoming neighbor, is revealing itself as a place where planets are under relentless pressure. The closer we listen to the quiet infrared whispers captured by James Webb, the clearer it becomes that this system is not gently cradling worlds. It is testing them, again and again, to see which can survive. That relentless testing is the true character of Alpha Centauri. It is not a single threat that makes this system dangerous, but the layering of many forces acting at once. Radiation, gravity, heat, and time all work together, slowly but inexorably shaping every world that tries to exist there. Around Alpha Centauri A and B, planets would face a different kind of hazard. These two stars orbit each other at distances that change over decades. When they draw closer, their combined gravity stirs the space around them. Any planet orbiting one of the stars feels not just one pull, but two, a constant tug of war that stretches and compresses its orbit. Over millions of years, that tugging can turn a once gentle circular path into a long and narrow ellipse. A planet on such an orbit swings close to its star and then far away, experiencing dramatic swings in temperature. Oceans can boil during close passes and freeze solid when the planet moves outward. Life, which depends on long-term stability, would struggle to adapt to such extremes. James Webb sees hints of this turmoil in the faint glow of dust around the stars. That dust is not static. It is being heated, pushed, and redistributed by the changing gravitational field. When scientists feed Webb's measurements into their models, they find that the habitable zones around Alpha Centauri A and B are not fixed rings like those around our Sun. They wobble and shift as the stars move, making it difficult for any planet to remain in the right place for long enough to allow life to gain a foothold. In our own solar system, the Sun sits alone. The orbits of the planets are nearly circular. The amount of sunlight Earth receives changes only slightly over the course of a year. This gentle regularity is one of the hidden reasons life has been able to thrive here for billions of years. Alpha Centauri does not offer that kind of peace. The final blow to the old dream of Alpha Centauri as a second home comes from the combined effect of all these forces. A planet there must survive intense stellar flares, powerful stellar winds, shifting habitable zones, and gravitational chaos. It must hold on to its atmosphere while being bombarded by radiation. It must maintain liquid water while its orbit is slowly being distorted. Each of these challenges alone would be formidable. Together, they make long-term habitability extraordinarily unlikely. James Webb did not find monsters or alien ruins in Alpha Centauri. What it is helping to reveal is something far more unsettling. The nearest stars to our own are not gentle suns quietly nurturing Earth-like worlds. They are engines of energy and instability, shaping their planets in harsh and unforgiving ways. Alpha Centauri remains a place of immense scientific interest. It is a natural laboratory for understanding how stars and planets interact under extreme conditions. But it is no longer the comforting symbol of a nearby paradise. It is a reminder that the universe does not owe us another home. As we look out across the vastness of space, it is tempting to assume that life must be common, that somewhere nearby another Earth is waiting. Alpha Centauri forces us to confront a harder truth. Even in the closest star system to our own, the conditions for life are fragile, fleeting, and easily destroyed. The stars that once seemed so welcoming now appear as they truly are: brilliant, beautiful, and profoundly indifferent to the survival of worlds around them. When James Webb was designed, it was not built to chase beauty, it was built to chase truth. Its giant golden mirror and delicate instruments were created for one purpose: to see the universe in the kind of light that human eyes never evolved to perceive. Infrared light carries the heat of worlds, the glow of dust, and the chemical fingerprints of atmospheres. It slips through clouds that block visible light. It reveals objects too cold and too faint for any telescope before it. And that is exactly why Alpha Centauri became one of the most important targets in modern astronomy. From Earth, Alpha Centauri looks simple: 3 stars shining quietly in the southern sky. But in infrared light, the system transforms. Dust glows, gas shines, invisible structures suddenly appear. These are the places where planets are born and destroyed. These are the environments that determine whether a world can ever become alive. James Webb was pointed toward this system not because scientists expected to see forests or oceans, but because they wanted to answer a deeper question. What does the nearest stellar neighborhood really look like when you strip away the comforting illusion of starlight and instead observe heat and chemistry? Proxima Centauri is the key. It is a red dwarf star, far cooler and dimmer than the Sun, but far more violent. Its light is faint in visible wavelengths, yet in infrared and high-energy radiation it is a raging furnace. Webb cannot stare directly at bright stars like Alpha Centauri A and B for long, but it can study the space around them. It can watch how dust and gas absorb and re-emit their heat. It can look for the subtle dips in light that suggest planets are passing in front of their stars. It can search for the spectral fingerprints of molecules that might be escaping from planetary atmospheres. Proxima b, the small rocky planet orbiting Proxima Centauri, became one of the most compelling targets in this effort. It is about the mass of Earth, and it sits in the region where liquid water could, in theory, exist. But theory is not enough. Many worlds occupy the right temperature zone and are still dead. What matters is whether they can hold on to air and water in the face of relentless stellar violence. James Webb was designed to read atmospheres from light. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's air before reaching the telescope. Different gases absorb different wavelengths. By splitting that light into a spectrum, Webb can tell which molecules are present. Carbon dioxide, methane, water vapor, oxygen, all leave distinct signatures. Even a thin atmosphere can announce its presence in this way. But Proxima b is a difficult target. Its star is active and noisy. Flares flood the system with bursts of radiation. The star's surface changes brightness constantly. This makes the delicate signals from a planet's atmosphere harder to isolate. Webb does not see a clean, steady light source. It sees a flickering storm. So scientists use Webb not just to look for atmospheres, but to measure the environment itself. How much infrared radiation is pouring out of the star? How much dust is being heated in the surrounding space? How often the star erupts? All of these data feed into models that simulate what Proxima b and any other planets in the system must be enduring. Alpha Centauri A and B offer another piece of the puzzle. Around them, Webb can detect the faint warmth of debris disks. These disks are made of tiny grains of rock and ice left over from planet formation. In a stable system, they settle into long-lasting belts. In a chaotic system, they collide, fragment, and glow brighter as they are constantly stirred. Webb sees that glow. It is a sign of motion, of energy, of disturbance. By combining these infrared observations with decades of data from other telescopes, scientists are building the most detailed picture ever of our nearest stellar neighbors. It is not a picture of tranquility. It is a picture of heat, motion, and relentless change. James Webb did not go to Alpha Centauri to find life directly. It went there to measure whether life could realistically survive. And the deeper it looks, the more it suggests that even in the closest star system to Earth, the universe is far less welcoming than we once hoped. James Webb works in a realm of light that feels almost supernatural. Infrared radiation is not something the human eye can see, yet it is everywhere. Every warm object in the universe glows in infrared. Planets glow, dust glows. Even the cold emptiness between stars glows faintly. This is the light of temperature and motion, and it is the language that Webb was built to understand. In a system like Alpha Centauri, this matters enormously. Visible light tells us where the stars are. Infrared light tells us what is happening around them. When dust grains collide, they heat up and release energy. When gas is stirred by gravity or radiation, it changes temperature. When a planet absorbs starlight and re-releases it, its thermal glow reveals its size and its surface conditions. Webb gathers all of this information and turns it into spectra that scientists can read like fingerprints. Around Proxima Centauri, those fingerprints are chaotic. The star pours out energy in irregular bursts. Its surface is covered in magnetic storms that twist and snap, releasing flares that can be more powerful than anything our own sun produces. Webb sees the aftermath of these flares in the way surrounding dust and gas, heat and cool. Each flare leaves a thermal echo that slowly fades, only to be replaced by the next eruption. By tracking these changes over time, scientists can estimate how often Proxima Centauri unleashes major storms. They can measure how much energy each one releases. From that, they can calculate how much radiation Proxima b is being exposed to. The numbers that come out of these models are staggering. A planet in such close orbit is bathed in levels of ultraviolet and X-ray radiation that would be lethal to unprotected life on Earth. James Webb also helps reveal something even more subtle. When radiation hits a planetary atmosphere, it does not just heat it, it can knock molecules apart. Ultraviolet light can split water vapor into hydrogen and oxygen. The lightweight hydrogen can then escape into space, slowly drying out a planet. Over millions of years, this process can strip away entire oceans. Webb looks for the spectral signs of such escaping gases. If hydrogen is streaming away from Proxima b, it would appear as a faint but telling signal in the infrared data. So far, the results suggest that if Proxima b has any atmosphere at all, it is fighting for its survival. The planet may need a powerful magnetic field to deflect the stellar wind, and even then, the constant flaring could overwhelm that protection. Without a magnetic shield, the atmosphere would be eroded even faster, leaving behind a barren, rocky surface. Around Alpha Centauri A and B, Webb tells a different, but equally troubling story. The dust disks around these stars are warmer and more dynamic than expected. This indicates frequent collisions between debris, a sign that the gravitational environment is stirring the material constantly. Planets forming in such a disk would be subjected to repeated impacts. Some of those impacts could be large enough to boil away oceans or strip atmospheres in a single event. What James Webb is really doing in Alpha Centauri is mapping risk. It is identifying all the ways a planet can fail to remain habitable: radiation, atmospheric escape, orbital instability, impact rates, thermal extremes. Each of these can be measured indirectly through infrared light, and each of them paints a picture of a system that is anything but gentle. The closer scientists look, the more Alpha Centauri seems less like a nearby refuge and more like a proving ground. Only the toughest worlds could endure such conditions, and even then, only for limited spans of time. Webb is showing us that proximity to Earth does not mean similarity to Earth. Our nearest neighbors may be radically different in all the ways that matter most for life. The most unsettling aspect of James Webb's work in Alpha Centauri is not what it sees, but what it fails to find. In a truly Earth-like system, infrared spectra would reveal stable, balanced atmospheres. There would be signs of water vapor cycling between surface and sky. There would be chemical hints of equilibrium, gases that persist over long periods without being torn apart by radiation or gravity. So far, nothing like that has emerged from the data. Instead, what appears again and again is variability. The thermal glow around Proxima Centauri flickers. The dust around Alpha Centauri A and B shifts in brightness. These are the signatures of systems in motion, systems being constantly reworked by forces far stronger than anything Earth experiences. This does not mean that life is impossible there. It means that life would have to be extraordinarily resilient, far more so than anything we know. It would need to survive radiation storms that could sterilize the surface. It would need to find refuge underground, or beneath thick layers of ice or water. It would need to evolve in an environment where the sky itself is a source of danger. James Webb is giving scientists the tools to move beyond hopeful speculation. For decades, the idea of a habitable Proxima b was based largely on its distance from its star. That was a single number, a simple calculation of heat. Webb adds dozens of new variables. It measures the star's output across a wide range of wavelengths. It reveals the structure of the surrounding space. It constrains the thickness and composition of any possible atmosphere. When all of those factors are combined, the picture becomes stark. A planet can sit in the right zone and still be unlivable. A system can be close and still be hostile. Alpha Centauri is not special because it is friendly. It is special because it shows us, in exquisite detail, how fragile habitability really is. This is why James Webb looked there, not to confirm our hopes, but to test them. Alpha Centauri is a mirror held up to our assumptions about life in the universe. What it reflects back is not comforting. It is a reminder that Earth may be far more unusual than we ever imagined. As the data continue to arrive and the models grow more sophisticated, the story of Alpha Centauri will keep evolving. But one thing is already clear. The nearest stars to our own are not quietly waiting for us to arrive. They are busy shaping and reshaping their worlds, indifferent to whether any of them can ever become alive. James Webb has turned our closest stellar neighbors into a case study in cosmic survival, and the lesson it is teaching is both awe-inspiring and deeply unsettling. Proxima Centauri belongs to a class of stars that dominate the galaxy. Red dwarfs are the most common type of star in the Milky Way. They are small, cool, and dim compared to the Sun, yet they burn for trillions of years. Because they live so long, they were once considered ideal hosts for life. More time means more chances for biology to emerge. But time is only helpful if the environment is not constantly trying to erase whatever forms. Red dwarfs are powered by intense magnetic fields. These fields are generated by the movement of hot plasma inside the star. In Proxima Centauri, those internal motions are extreme. The star spins quickly, twisting its magnetic field into a tangled web. When those magnetic lines snap and reconnect, they release enormous amounts of energy in the form of flares. A single major flare from Proxima Centauri can release more energy than the Sun does in several days. In ultraviolet and X-ray light, these flares can be hundreds or thousands of times brighter than the star's normal output. For a planet like Proxima b, orbiting very close to the star, each flare is like a cosmic lightning strike. James Webb does not observe ultraviolet or X-rays directly, but it sees their effects. When a flare erupts, it heats the surrounding dust and gas. That heat lingers, glowing in infrared light long after the initial burst has faded. By watching these afterglows, Webb helps scientists reconstruct how often Proxima Centauri flares and how powerful those flares are. The pattern that emerges is alarming. Proxima Centauri is not a star that flares occasionally. It flares constantly. Some eruptions are small, others are enormous. Many are so intense that they would strip the ozone layer from Earth if our planet were placed in the same position as Proxima b. Ozone is important because it blocks harmful ultraviolet radiation. Without it, the surface of a planet is exposed to radiation that damages DNA and disrupts the chemistry of life. Even if Proxima b started with an Earth-like atmosphere, repeated flares could erode its protective layers, leaving the surface exposed to lethal levels of radiation. There is another danger hidden in these storms. When Proxima Centauri flares, it also releases a flood of charged particles. This is known as stellar wind. These particles slam into any nearby planet. If the planet does not have a strong magnetic field, the wind can peel away its atmosphere like a slow cosmic sandblaster. Mars provides a sobering example. Long ago, Mars had rivers and lakes, but it lost most of its magnetic field. The sun's wind then stripped away much of its atmosphere, turning it into the cold, dry world we see today. Proxima b faces a similar threat, but on a far more intense scale. Because Proxima Centauri is so active, its stellar wind is much stronger than that of the Sun. A planet so close to the star is constantly being battered. To survive, Proxima b would need a magnetic field far stronger than Earth's. Even then, the repeated impacts of radiation and particles could overwhelm it. Red dwarfs like Proxima Centauri were once seen as gentle and long-lived. James Webb and other modern observatories are revealing their darker side. They are not just dim suns, they are engines of magnetic violence, bathing their planets in radiation and storms. This changes how scientists think about habitability across the galaxy. If most stars are red dwarfs, and if most red dwarfs behave like Proxima Centauri, then many of the planets we once thought might be friendly could in fact be hostile. The galaxy may be filled with worlds that sit in the right temperature range, but are relentlessly sterilized by their own stars. Proxima Centauri is the closest example of this reality. It is a laboratory just 4.37 light-years away, showing us what life would have to endure around a red dwarf. And what it shows is not comforting. The violence of a red dwarf star is not a rare event. It is the normal state of being. Proxima Centauri spends much of its life in a state of magnetic unrest. Its surface is covered in regions where magnetic energy is trapped and twisted. When that energy is released, it does not trickle out gently, it explodes. These explosions do not just happen on the star, they ripple outward through space. High-energy photons race ahead, followed by clouds of charged particles. When they reach a planet, they interact with its atmosphere in destructive ways. Molecules are broken apart, ions are created. The upper layers of air can be heated so much that they begin to escape into space. James Webb helps scientists quantify this process by observing the thermal and chemical changes in the region around Proxima Centauri. When flares occur, Webb can detect shifts in the infrared signatures of surrounding gas. These shifts indicate heating and expansion, a sign that energy is being dumped into the environment. From this, researchers can estimate how much energy is reaching Proxima b. One of the most troubling findings from these studies is how quickly a red dwarf can strip a planet. In simulations informed by Webb data, A planet like Proxima b could lose an Earth-like atmosphere in just a few 100 million years. That might sound like a long time, but in the life of a star it is a blink. On Earth, life took longer than that to become complex. If Proxima b lost its air that quickly, it may never have had a chance. Some scientists argue that if Proxima b has a very thick atmosphere or a powerful magnetic field, it could survive. But both of those conditions are uncertain. A thick atmosphere would be heavy and might trap heat, turning the planet into a kind of runaway greenhouse. A powerful magnetic field requires a molten and active core, which in turn depends on the planet's composition and history. We do not know if Proxima b has these things. What we do know is that Proxima Centauri is relentless. It does not give its planets long periods of calm. There is no long quiet phase in which life could gently evolve. Instead, there are bursts of energy, again and again, each one chipping away at whatever fragile balance might exist. This is why the red dwarf problem has become one of the central questions in astrobiology. These stars are everywhere. Most of the potentially habitable planets discovered so far orbit red dwarfs. If their environments are as harsh as Proxima Centauri's, then the universe may be full of planets that look promising on paper, but are sterile in reality. James Webb is not just studying Alpha Centauri, it is helping scientists rewrite their expectations for life in the cosmos. By revealing the true behavior of red dwarfs, it is showing that habitability is not just about distance from a star, it is about stability, protection, and time. Proxima b sits in a storm. It may have water, it may have rock and soil, but it is also being bombarded by forces that could erase those conditions over and over again. The violent reality of red dwarfs turns what once seemed like a hopeful discovery into a sobering cautionary tale. The final and perhaps most unsettling consequence of this red dwarf violence is how it shapes the long-term fate of planets like Proxima b. Even if such a world began with oceans and a thick atmosphere, even if it had all the raw ingredients for life, those conditions would be under constant attack. Every flare strips a little more air away. Every burst of radiation breaks a few more molecules apart. Over time, the planet is slowly bled dry. James Webb data allow scientists to model this erosion with increasing precision. By measuring how much energy Proxima Centauri emits across different wavelengths, researchers can estimate how fast a planetary atmosphere would be lost. The results suggest that without extraordinary protection, Proxima b would become a barren rock on timescales far shorter than the age of the star. There is also the issue of surface radiation. Even if some atmosphere remains, it may not be enough to shield the surface. Ultraviolet light can penetrate thin atmospheres and sterilize exposed ground. X-rays can reach deep into soil and water. Any life on the surface would be constantly threatened. Only organisms hidden underground or beneath thick layers of ice or ocean might survive. If at all, this leads to a haunting possibility. Proxima b could be a world where life once tried to begin, only to be wiped out repeatedly by stellar storms. It could be a planet of ghosts, where the conditions for life flicker briefly and then vanish. Red dwarfs live for trillions of years. Proxima Centauri will still be shining long after the sun has burned out. But a long-lived star does not guarantee a long-lived biosphere. In fact, the early violent phases of red dwarfs may make them some of the worst places for life to get started. Alpha Centauri, because it is so close, allows us to see this reality in detail. It is not an abstract model or a distant speculation. It is right there, 4.37 light-years away, showing us how unforgiving a star can be to its planets. James Webb is turning that realization into hard data. With every observation, it adds weight to the idea that many worlds we once hoped for may be far less friendly than they appear. The violent reality of red dwarfs is rewriting our map of the habitable universe, and if even our nearest red dwarf neighbor is this hostile, it raises a chilling question. How many of the countless red dwarf planets scattered across the galaxy are truly alive? And how many are simply enduring a long, slow march toward lifelessness? An atmosphere is more than air. It is a shield, a thermostat, and a chemical engine. On Earth, it protects life from radiation, keeps the planet warm, and allows water to exist as liquid. Without it, our world would look more like the Moon or Mars, cold, dry, and dead. When scientists ask whether a planet can be habitable, the first question they ask is not about temperature, it is about whether the planet can hold on to its atmosphere. In Alpha Centauri, that question becomes brutally difficult. Proxima Centauri's constant flaring and powerful stellar wind act like a blowtorch on any nearby world. Alpha Centauri A and B, though calmer, still generate strong winds and radiation. The combined effect of these forces makes it extremely hard for planets in this system to keep their air. James Webb was built to detect atmospheres from across the galaxy. It does this by reading the way light changes as it passes through a planet's air. Different gases absorb different wavelengths, creating patterns that Webb can see in infrared spectra. Even a thin atmosphere leaves a trace. A thick one leaves a strong signal. So far, when scientists look at the Alpha Centauri system with Webb and with other telescopes, those signals are elusive. Proxima b has not yet revealed a clear atmospheric fingerprint. This could mean that the planet has no atmosphere. It could mean that the atmosphere is too thin to detect. Or it could mean that it is constantly changing, being stripped away and replenished by volcanic gases in a desperate balance. What we do know is that Proxima Centauri's wind is strong enough to remove air far more quickly than the Sun's wind removes air from Earth. A planet in such an environment must have exceptional defenses. A strong magnetic field can help deflect charged particles, but it cannot stop high-energy radiation. Ultraviolet and X-rays can penetrate deep into the upper atmosphere, heating it and causing it to expand. When it expands, it becomes easier for gas to escape into space. This process is called atmospheric escape. It is slow, but it is relentless. Over millions of years, even a massive atmosphere can be whittled down to nothing. James Webb helps scientists estimate how fast this is happening by measuring the energy input from the star and the likely composition of the planet's air. There is also the issue of chemistry. Radiation changes what an atmosphere is made of. It can destroy ozone. It can split water vapor. It can create reactive molecules that eat away at other gases. A stable, life-supporting atmosphere requires a delicate balance of chemical reactions. Proxima Centauri's radiation constantly disrupts that balance. Around Alpha Centauri A and B, the situation may be slightly better, but not by much. Their combined gravitational and radiation environment still poses a challenge. Planets there would need to survive not only stellar wind, but also the shifting habitable zone caused by the star's orbit. If a planet moves closer or farther from its star over time, its atmosphere can freeze or boil, further destabilizing it. The atmosphere problem is the quiet killer of habitability. A planet can be in the right place, with the right size and the right temperature, and still fail if it cannot keep its air. Alpha Centauri, once seen as a beacon of possibility, is now revealing just how fragile that air really is. Atmospheric loss is not always dramatic. There is no single moment when a planet suddenly goes from blue and cloudy to barren. Instead, there is a slow, invisible erosion. Molecules rise, are struck by radiation, and drift away into space. Over thousands of years, the effect is small. Over millions, it becomes significant. Over hundreds of millions, it can transform a world. James Webb gives scientists a way to measure this erosion without ever seeing the planet directly. By observing the infrared glow of the star and its surroundings, Webb can estimate how much energy is being deposited into a planet's upper atmosphere. It can also look for the faint signatures of gases that have been broken apart, such as hydrogen and oxygen. When water vapor is split by radiation, the hydrogen is light enough to escape easily. If Webb detects an excess of hydrogen around Proxima Centauri, it is a clue that water is being lost from nearby planets. This is not just theory. Similar processes have been observed around other red dwarf stars. Some exoplanets show enormous tails of gas streaming away from them, like comets made of air. Those tails are the visible signs of atmospheres being stripped. Alpha Centauri is close enough that Webb can search for subtler versions of these effects. So far, nothing has been seen that would indicate a thick, stable atmosphere around Proxima b. That absence is telling. It suggests that if an atmosphere exists, it is either thin, transient, or composed of unusual gases that do not show up strongly in the infrared. None of these scenarios is encouraging for life. The loss of an atmosphere has cascading effects. Without air, A planet cannot regulate its temperature. Heat from the star is absorbed directly by the surface during the day and radiated away at night. On a tidally locked world like Proxima b, this would mean a blazing hot dayside and a frozen nightside. Winds that might otherwise redistribute heat are absent or weak. The planet becomes a place of extremes. Without an atmosphere, liquid water cannot exist on the surface. It would either boil away or freeze. Even underground, water would be difficult to maintain over long periods. Life, as far as we know it, needs liquid water. The atmosphere is what makes that possible. Alpha Centauri A and B might host planets with thicker atmospheres, but the binary nature of the system complicates things. Gravitational interactions can cause variations in a planet's orbit that lead to cycles of heating and cooling. During warmer phases, gases can escape more easily. During colder phases, they can condense or freeze out. Over time, this cycling can also erode an atmosphere. James Webb is helping scientists understand these long-term processes. By mapping the infrared environment of the system, it reveals how energy flows through it. That energy is the driver of atmospheric change. The more chaotic the energy flow, the harder it is for a planet to maintain equilibrium. The atmosphere problem is what turns many potentially habitable worlds into barren rocks. Alpha Centauri, despite its proximity and its sun-like stars, appears to be a place where that problem is severe. It is not enough to be close to a star. A planet must be protected from it. The deeper scientists look into Alpha Centauri, the more the atmosphere problem begins to feel like a nearly insurmountable barrier. A planet must not only start with enough gas and water, it must keep them through a lifetime of stellar assault. In a system as active and complex as this one, that is a rare achievement. James Webb is showing us that the story of habitability is written in infrared light. Where energy flows gently, atmospheres can persist. Where energy surges violently, they are stripped away. Alpha Centauri is flooded with energy. Proxima Centauri, in particular, pours out radiation and stellar wind that relentlessly attacks any nearby planet. Even if Proxima b somehow retains a thin atmosphere, it may not be the kind of atmosphere that supports life. High radiation can drive chemical reactions that create toxic gases. It can destroy ozone and allow ultraviolet light to reach the surface. It can produce a haze that blocks visible light, plunging the surface into dimness, even on the day side. There is also the question of replenishment. On Earth, volcanic activity releases gases that help rebuild the atmosphere over time. Plate tectonics recycle carbon and water, but on a small rocky planet orbiting a red dwarf, those processes may not be strong or long-lived. If Proxima b's interior has cooled and solidified, it may no longer be able to replace the air it loses. Around Alpha Centauri A and B, any planets would face a different, but still serious challenge. The shifting gravitational environment can trigger periods of intense heating. During those times, an atmosphere can expand and leak away more rapidly. Once lost, it is difficult to get back. James Webb is not yet able to tell us exactly how thick or thin these atmospheres are, but it is already telling us something just as important. It is telling us that the conditions needed to preserve an atmosphere in Alpha Centauri are extreme. They require strong magnetic fields, stable orbits, and favorable stellar behavior all at once. That combination may be rare. This is the quiet tragedy of many worlds. They may begin with all the ingredients for life, but they lose the one thing that makes those ingredients usable. Air is invisible, but without it, a planet is dead. Alpha Centauri is teaching us that proximity does not equal safety. Even the stars nearest to our own can be hostile to the fragile shells of gas that make planets alive. And if that is true here, so close to Earth, it may be true across much of the galaxy. Radiation is the most silent threat in space. You cannot see it, you cannot hear it, you cannot feel it until it has already done its damage. Yet it is one of the most powerful forces shaping whether a planet can remain alive. In Alpha Centauri, radiation is not a background presence, it is a constant storm. Every star emits radiation, including our own sun. But Proxima Centauri, and even Alpha Centauri A and B, do so in far more aggressive ways. High-energy light in the form of ultraviolet and X-rays pours out during stellar flares. These rays slice through space at the speed of light. When they strike a planet, they penetrate deep into its atmosphere and sometimes all the way to the surface. James Webb helps scientists understand this invisible danger by measuring how energy is distributed throughout the system. When radiation hits dust and gas, it heats them. That heat glows in infrared light, which Webb can detect. By mapping that glow around Proxima Centauri, researchers can see how often powerful bursts of energy are sweeping through the region where Proxima b orbits. The results are deeply unsettling. Proxima Centauri unleashes radiation storms so frequently that Proxima b rarely experiences a true calm. On Earth, our magnetic field and thick atmosphere absorb most of the harmful radiation from the Sun. They create a safe bubble where life can exist on the surface. Proxima b may not have such protection. If radiation reaches the surface of a planet, it damages the molecules that make life possible. It breaks apart DNA. It disrupts proteins. It alters chemical reactions in ways that make biology unstable. Even simple microbes struggle to survive in high radiation environments. Complex life is even more vulnerable. On Proxima b, the radiation environment is likely far harsher than anything on Earth. During major flares, the star can become thousands of times brighter in high-energy light. Those bursts could bathe the entire planet in levels of radiation that would be lethal to most known forms of life. Even oceans may not be safe. Water can absorb some radiation, but high-energy rays can penetrate surprisingly deep. In extreme conditions, even a few meters of water may not be enough to provide full protection. Life would need to hide beneath thick layers of rock or ice to survive, if it can survive at all. Alpha Centauri A and B are less violent than Proxima Centauri, but their radiation still matters. They emit ultraviolet light that can erode atmospheres and damage surface chemistry. In a binary system, the combined radiation environment is complex and variable. Planets may be exposed to changing levels of high-energy light as the stars move in their orbit. James Webb is helping scientists map this radiation indirectly by watching how the system glows in infrared. Where energy is deposited, heat follows. That heat reveals where radiation is striking and how intense it is. The patterns that emerge suggest a system that is anything but gentle. Radiation is the invisible killer of habitability. A planet can have the right temperature and even the right amount of water, but if it is constantly being bathed in lethal energy, life has no chance to persist on the surface. Alpha Centauri is showing us just how dangerous a nearby star can be. Radiation does more than harm living cells. It reshapes entire planetary environments. When high-energy light strikes an atmosphere, it changes the chemistry of the air. It can break stable molecules into reactive fragments. It can destroy ozone, which is one of the most important shields against ultraviolet light. Without ozone, even more radiation reaches the surface, creating a feedback loop of damage. James Webb helps scientists trace this process by looking for the spectral signatures of different gases. If ozone or water vapor is being broken apart, their chemical fingerprints weaken. If new reactive gases are being created, their signatures appear. Around Proxima Centauri, these patterns suggest an atmosphere that is constantly being chemically battered. There is also the problem of secondary radiation. When high-energy particles from a stellar flare hit a planet's atmosphere, they can create showers of new particles that cascade down toward the surface. This is similar to what happens when cosmic rays strike Earth. But on Proxima b, it would be far more intense. These particle showers can penetrate deep into soil and water, spreading radiation far beyond the upper atmosphere. Even a magnetic field cannot stop all of this. A magnetic field deflects charged particles, but high-energy photons, like X-rays and ultraviolet light, pass through magnetic shields easily. Only a thick atmosphere can absorb them, and only if that atmosphere remains intact. In the Alpha Centauri system, the radiation environment is made worse by variability. The stars do not shine at a steady output. They flare, they quiet down, they flare again. This means that a planet is subjected to sudden spikes of radiation that are far more damaging than a constant, steady flow. Biology can sometimes adapt to stable, harsh conditions. It struggles to survive unpredictable extremes. On Earth, the worst radiation events from the sun are rare and usually mild. our planet has had billions of years of relatively stable conditions. In Alpha Centauri, especially around Proxima Centauri, that stability does not exist. The radiation climate is wild and erratic. James Webb is helping scientists quantify just how wild it is. By observing the infrared afterglow of flares and the heating of surrounding material, Webb reveals how much energy each event releases. From that, researchers can estimate the radiation dose a planet like Proxima b receives. The numbers point to a world under constant assault. This does not completely rule out life. It suggests that any life would have to be deeply sheltered. It might exist underground or beneath thick ice. It might be microbial and slow-growing, but the idea of a lush Earth-like biosphere under an open sky becomes increasingly unlikely. Alpha Centauri is close enough that these conclusions are not abstract. They are based on real data, real light captured by James Webb. The invisible killer is being made visible, and it is telling a grim story. The long-term effect of this radiation is not just a series of lethal moments, it is a gradual transformation of the planet itself. Over millions of years, radiation changes the surface, the atmosphere, and even the interior. Rocks become chemically altered, gases are lost, water is broken apart. The planet slowly drifts away from anything that could support life. James Webb observations suggest that Proxima b exists in a radiation environment that is far harsher than anything Earth has ever experienced. Even during relatively quiet periods, the background level of high-energy light is elevated. During flares, it becomes extreme. If Proxima b has a magnetic field, it is under constant strain. If it does not, its atmosphere and surface are exposed directly. This means that even if life somehow began on Proxima b, it would face an uphill battle to survive. It would need to adapt to frequent radiation storms. It would need to repair its DNA constantly. It would need to hide. Evolution might find a way, but the odds are not in its favor. Alpha Centauri A and B present a slightly different picture. Their radiation is less intense, but the binary nature of the system introduces long-term variability. Planets orbiting these stars could experience cycles of increased radiation as the stars move closer together and then farther apart. Those cycles could stress atmospheres and biospheres in ways that are difficult to survive. The invisible killer is not just about individual flares, it is about the overall radiation climate of a system. Alpha Centauri, as revealed by James Webb and other observatories, appears to be a harsh climate for life. This realization changes how scientists think about nearby stars. It is not enough to count planets in the so-called habitable zone. We must ask what those planets are being exposed to. Radiation, more than temperature, may be the deciding factor. Alpha Centauri is no longer just our nearest neighbor. It is a warning. It shows us that even close, familiar stars can create environments that are profoundly hostile to life. One of the most subtle and devastating forces acting on planets around red dwarf stars is not radiation or stellar wind, it is gravity. Proxima b orbits extremely close to Proxima Centauri, so close that the difference in gravitational pull between the near side and the far side of the planet is enormous. Over time, that difference acts like a brake on the planet's rotation. The planet slows, wobbles, and eventually becomes tidally locked, always showing the same face to its star. This is not speculation. The laws of physics make it almost inevitable for a planet in such a tight orbit. The Moon is tidally locked to Earth. One side always faces us. Proxima b is in a far more extreme situation. Its year lasts only about 11 Earth days. That means it spins in the grip of Proxima Centauri's gravity constantly. The end result is a world split in two. On the side that faces the star, daylight never ends. Proxima Centauri hangs in the sky, red and bright, pouring heat and radiation onto the surface. Rocks bake. Any exposed water would either evaporate or be broken apart by ultraviolet light. Temperatures could reach levels that turn the ground into a dry and hostile desert. On the opposite side, night never ends. Without sunlight, the surface loses heat to space. Temperatures plunge. Any water freezes solid. Gases in the atmosphere, if any remain, can condense and fall as snow or frost. Over time, the night side can become a trap where the atmosphere itself freezes out, leaving even less air to circulate. Between these two extremes lies a narrow band of twilight, a ring around the planet where the sun sits low on the horizon. This region is often imagined as the only potentially habitable zone on a tidally locked world. In theory, temperatures there could allow liquid water. But theory does not account for all the other forces at play. James Webb helps scientists model how heat moves on such a planet. By measuring the infrared output of the star and the surrounding space, researchers can estimate how much energy reaches Proxima b and how that energy might be redistributed by winds. If the planet has a thick atmosphere, winds could carry heat from the day side to the night side, softening the extremes. If the atmosphere is thin, that redistribution would be weak, and the planet would remain a world of fire and ice. The radiation environment makes this even worse. The day side is not just hot, it is constantly being blasted by stellar flares. The night side is shielded from direct radiation, but it is also starved of heat. Life, if it exists, would have to cling to the narrow twilight zone, enduring violent storms from one side and freezing darkness from the other. Tidal locking also affects the planet's interior. The constant gravitational pull can create tidal heating, flexing the planet and generating internal heat. This can drive volcanism, which might replenish an atmosphere but also makes the surface unstable. Volcanoes release gases, ash, and lava, creating a dynamic but dangerous environment. So Proxima b is caught in a trap. It is close enough to be warm, but too close to be safe. It is held in a permanent gravitational embrace that splits it into two worlds, neither of which is friendly to life as we know it. Alpha Centauri, A and B, may host planets that are not tidally locked, but their binary nature creates its own gravitational traps. Orbits can be distorted, rotations can be altered, stability is rare. James Webb is revealing that gravity itself is one of the greatest enemies of habitability. It shapes planets into forms that may look promising from afar, but are deeply hostile up close. The tidal locking trap is yet another way that Alpha Centauri undermines the dream of a nearby second Earth. When scientists first realized that Proxima b was likely tidally locked, some hoped that a thick atmosphere or a global ocean could save it. Water and air can transport heat. They can blur the line between day and night. In the most optimistic models, the dayside heat would drive winds that sweep warmth across the planet, preventing the night side from freezing completely. In those models, the twilight band could widen, creating a larger region where life might survive. James Webb has given those models something real to work with. By measuring the infrared energy around Proxima Centauri, scientists can estimate how much heat is available to be redistributed. They can also constrain how thick an atmosphere would need to be to move that heat effectively. The results are sobering. To balance the extremes, Proxima b would need an atmosphere far denser than Earth's. Such a dense atmosphere would trap heat and could lead to a runaway greenhouse effect, cooking the planet even in the twilight zone. There is also the problem of clouds. On a tidally locked planet, clouds would likely form on the day side, where warm, moist air rises. Those clouds could reflect some sunlight, cooling the surface. But Proxima Centauri's flares complicate this. High-energy radiation can destroy cloud-forming molecules and break apart water vapor. The cloud cover would be unstable, waxing and waning with each stellar storm. The night side presents a different hazard. In perpetual darkness, temperatures drop low enough that gases can freeze. Carbon dioxide, nitrogen, even oxygen can condense if it gets cold enough. When that happens, the atmosphere literally falls out of the sky, piling up as ice on the night side. Over time, this can thin the atmosphere globally, weakening its ability to transport heat and protect the surface. This creates a feedback loop. A thinner atmosphere means less heat transport, which means a colder night side, which leads to more atmospheric freeze-out. Eventually, the planet can be left with most of its air locked away as ice, leaving the rest of the world exposed. James Webb observations suggest that Proxima b does not have the kind of thick, stable atmosphere that would be needed to avoid this fate. The infrared signatures simply are not there. If air exists, it is likely thin and vulnerable. Tidal locking also affects weather. Winds would be driven from the hot day side to the cold night side at high speeds. These winds could reach velocities far beyond anything on Earth. Such constant storms would erode the surface and stir the atmosphere violently. Combined with radiation and stellar wind, this would make the environment even harsher. So the narrow twilight band, once imagined as a refuge for life, becomes a turbulent and unstable region. It is squeezed between heat and cold, battered by wind and radiation. Life there would not find a gentle cradle. It would find a battlefield. Proxima b is a world shaped by extremes. Its position in the habitable zone hides the deeper truth of its environment. James Webb is helping us see that truth. It is a planet caught between fire and ice, under a sky that never rests. The more deeply scientists explore the tidal locking of Proxima b, the more it becomes clear that this single factor amplifies every other danger. Radiation, atmospheric loss, and thermal extremes all feed into one another, creating a system that is extraordinarily difficult for life to navigate. On the day side, the constant heat and radiation would likely destroy organic molecules faster than they could form. Even simple compounds could be broken apart before they have a chance to participate in the chemistry of life. On the night side, cold temperatures slow chemical reactions to a crawl. In the twilight zone, where conditions might be moderate, the environment is unstable, shaped by violent winds and shifting clouds. James Webb gives scientists a way to simulate these conditions with unprecedented accuracy. By feeding Webb's infrared measurements into climate models, researchers can explore how a planet like Proxima b would behave under such stresses. The results consistently show narrow, habitable regions that are fragile and transient. Small changes in stellar activity or atmospheric thickness can push the planet from barely tolerable to completely hostile. There is also the question of water. On a tidally locked world, liquid water would tend to migrate. On the day side, it would evaporate. On the night side, it would freeze. Over time, most of the planet's water could end up locked away as ice in the dark hemisphere, leaving the rest of the surface dry. This process, sometimes called cold trapping, would deprive the twilight zone of one of the most important ingredients for life. Even if some water remains in liquid form, it would likely be subject to extreme cycles. Periods of evaporation and freezing would concentrate salts and other chemicals, making the water less hospitable to biology. The chemistry of life requires not just water, but relatively stable water. All of these challenges make Proxima b a far cry from a second Earth. It is a world where every advantage is offset by a disadvantage, where every potential refuge is under threat. Alpha Centauri A and B offer no easy escape from this reality. Planets around them may avoid tidal locking, but they face the gravitational and radiation challenges of a binary system. There is no simple safe haven in this stellar neighborhood. James Webb is not destroying our dreams of nearby life. It is refining them. It is showing us that habitability is a narrow and delicate condition, not a broad and forgiving one. Proxima b and the rest of Alpha Centauri are teaching us that the universe does not easily give rise to Earth-like worlds. The tidal locking trap is just one more piece of that lesson, a reminder that even a planet in the right place can be shaped into something profoundly inhospitable by the quiet, relentless pull of gravity. Alpha Centauri A and Alpha Centauri B do not exist in isolation the way our Sun does. They are bound together in a long gravitational embrace, circling one another through space in a slow and relentless dance that has been going on for billions of years. Every 80 Earth years or so, they complete one full orbit around their shared center of mass. During that time, the distance between them changes dramatically. Sometimes they draw closer, sometimes they drift farther apart. That motion might seem gentle on a human timescale, but on the scale of planets, it creates a powerful and constantly shifting gravitational field. In a single star system like our own, gravity is simple. The Sun dominates, and the planets move in nearly stable and predictable paths. In a binary system, gravity is complicated. A planet orbiting Alpha Centauri A feels the pull of its own star, but it also feels the pull of Alpha Centauri B. That second tug is weaker, but it is never absent. As the two stars move in their orbit, the strength and direction of that tug change. Over time, those small changes accumulate. James Webb allows scientists to see the fingerprints of this gravitational chaos in infrared light. Around Alpha Centauri A and B lie vast disks of dust and debris. These disks are not just leftovers from planet formation. They are active, dynamic structures that glow because they are constantly being stirred and heated by collisions. When two dust grains crash into each other, they release energy. That energy shows up as warmth, and warmth glows in infrared. Webb sees these glowing patterns, mapping where collisions are happening most often. Those collisions are not random, they are driven by gravity. The shifting pull of the two stars perturbs the orbits of tiny particles and larger bodies alike, forcing them into paths that cross and collide. If this is what happens to dust, it also happens to planets. Worlds forming in such an environment are born into instability. A planet that starts on a nearly circular orbit around Alpha Centauri A may slowly be stretched into a more elongated path by the distant but persistent tug of Alpha Centauri B. Over millions of years, that elongation can become severe. When the planet swings close to its star, it is blasted with heat and radiation. When it swings far away, it cools dramatically. These cycles are far more extreme than anything Earth experiences. Such temperature swings place enormous stress on a planet's atmosphere. During close approaches, gases heat up and expand, making it easier for them to escape into space. During distant phases, those same gases can cool and condense. Over time, this repeated expansion and contraction can bleed an atmosphere away. James Webb data helps scientists estimate how much energy these planets would be exposed to during different phases of their orbits, making it possible to model how quickly their atmospheres would erode. The chaos does not stop there. The gravitational interaction between Alpha Centauri A and B can also trigger orbital resonances. These are situations where the orbital periods of planets line up in ways that amplify their gravitational interactions. Resonances can pump energy into a system, increasing orbital eccentricity and tilting planetary axes. On Earth, even small changes in tilt and orbit affect climate. In Alpha Centauri, those changes could be far more dramatic. Over long periods, this instability can lead to catastrophic outcomes. A planet might be nudged into a collision with another world. It might spiral inward toward its star, becoming a scorched remnant. Or it might be ejected entirely, cast out into the cold emptiness between stars. James Webb cannot watch these events directly, but the infrared glow of disturbed dust and debris tells us that the system is still being reshaped. Even the habitable zones around Alpha Centauri A and B are not fixed. As the stars move closer and farther apart, their combined radiation changes. This shifts the region where liquid water could exist on a planet's surface. A world that sits comfortably in that zone for a few million years could later find itself too hot or too cold. Life requires long periods of stability to take hold. Alpha Centauri offers anything but stability. This is what makes binary star systems so dangerous for habitability. They are not just brighter versions of single stars. They are dynamic engines of gravitational change. Every planet in their domain is constantly being tested, pushed, and pulled in ways that make long-term equilibrium rare. James Webb is revealing this through quiet light, through the faint warmth of dust and the subtle glow of disturbed material. Those infrared signals are the footprints of chaos. They tell us that Alpha Centauri A and B are not peaceful suns gently hosting their planets. They are partners in a gravitational dance that keeps their entire system in motion. When a planetary system exists around a pair of stars like Alpha Centauri A and B, the danger is not always immediate. The most destructive effects often unfold slowly, across tens of millions or even hundreds of millions of years. This slow-motion destruction is what makes binary star chaos so deceptive. A planet can appear stable for a long time, only to be gradually pushed into a state that makes life impossible. James Webb helps scientists see the early warning signs of this instability by measuring how dust and debris behave over time. In a calm system, dust settles into thin, orderly rings. In Alpha Centauri, the dust appears thicker and more irregular. That irregularity is a signal of constant gravitational stirring. Every small shift in the orbit of Alpha Centauri, A or B, changes how particles move. Over time, those shifts propagate outward, affecting larger and larger bodies. Planets forming in such an environment face a difficult childhood. Their orbits are not allowed to settle into gentle, circular paths. Instead, they are nudged and tugged by the gravitational rhythm of the two stars. This can tilt their axes, leading to extreme seasons. It can stretch their orbits, leading to wild swings in temperature. It can even destabilize their spin, making their climate unpredictable. Imagine a planet that begins with oceans and a thick atmosphere. During one phase of its orbit, it might be warm enough for liquid water to exist. During another, it might become so cold that much of that water freezes. During a hotter phase, water vapor could rise into the atmosphere and be broken apart by radiation, allowing hydrogen to escape. Over many cycles, this process could dry the planet out. James Webb data, when fed into long-term simulations, suggest that such cycles are likely in the Alpha Centauri system. The combined gravitational influence of the two stars creates a complex web of resonances that can alter planetary orbits over time. Even small changes, repeated again and again, can transform a once habitable world into a barren one. The chaos also affects how often planets are struck by asteroids and comets. In a disturbed system, small bodies are more likely to be thrown into crossing orbits. This increases the rate of impacts. Some impacts can be beneficial, delivering water and organic molecules, but too many large impacts can sterilize a planet's surface, boiling away oceans and stripping atmospheres. Alpha Centauri appears to be a system where such impacts may be more common. James Webb sees hints of this in the infrared glow of dust created by collisions. That dust is not ancient and settled. It is being continually replenished by ongoing impacts. This suggests that the system is still dynamically active, even billions of years after its formation. For life, this is bad news. Life needs not only the right ingredients but also time. It needs millions of years of relative calm to evolve complexity. In Alpha Centauri, that calm may be constantly interrupted by gravitational and collisional upheaval. So while Alpha Centauri A and B may look like comforting twins of our own sun, their partnership makes their planetary environment far more hostile. They create a landscape of shifting gravity, changing radiation, and frequent impacts. It is a place where worlds are never truly at rest. The final layer of danger in a binary star system like Alpha Centauri A and B is how all of these forces combine. Gravity does not act alone. Radiation, stellar wind, and orbital instability feed into each other, creating a system where small changes can have enormous consequences over time. James Webb shows that the dust around Alpha Centauri is not evenly distributed. Some regions glow brighter, indicating clusters of collisions and heating. These are zones where gravity is forcing material into chaotic motion. In a young system, such chaos might settle down as planets clear their orbits. In Alpha Centauri, the chaos appears to persist, suggesting that the gravitational tug of the two stars continues to stir the system. This persistent stirring means that any planet trying to maintain a stable orbit is constantly being nudged. Those nudges might seem tiny, but over millions of years, they accumulate. A planet's orbit can slowly drift inward or outward. Its tilt can change. Its climate can be pushed from one regime to another. A world that begins as a potential haven can become a frozen wasteland or a scorched desert without ever experiencing a single dramatic catastrophe. The habitable zones around Alpha Centauri A and B are therefore not safe harbors. They are moving targets. A planet might spend a short geological moment in a comfortable range of temperatures, only to be pushed out of it by the slow dance of the stars. Life, if it began, would be forced to adapt to conditions that never remain constant for long. James Webb is revealing this reality, not through direct images of planets, but through the environment in which those planets must exist. The infrared glow of dust and debris is the signature of motion and instability. It is the background against which all worlds in the system must struggle. Alpha Centauri A and B remind us that stars do not exist in isolation. Their relationships shape the fate of everything around them. In this system, the relationship is one of perpetual motion and change. When scientists once imagined Alpha Centauri as a second home, they were thinking of stars like our sun, calm and steady. James Webb is showing us that even stars that look similar can behave very differently when paired together. The chaos of binary stars may be one of the most powerful barriers to habitability in the universe. This brings us to a sobering conclusion. Alpha Centauri, despite its closeness and its sun, like stars, is not a quiet refuge. It is a restless system where gravity and radiation work together to make life difficult to sustain. The nearest stellar neighbors to Earth are not welcoming. They are teaching us how rare and precious a stable environment like our own truly is. By the time James Webb began returning its detailed infrared measurements of the Alpha Centauri system, scientists were prepared for surprises. They were not prepared for how consistently harsh those surprises would be. Webb did not reveal oceans or gentle cloud decks. It revealed energy, motion, and instability. Around Proxima Centauri, Webb detected complex patterns of infrared emission that shift over time. These patterns trace how dust and gas heat up after stellar flares and then slowly cool. Each brightening is the echo of a burst of radiation that swept through the system. When these data are stacked over months of observation, they form a record of just how often Proxima Centauri erupts. The frequency is high. The star is rarely quiet. These infrared echoes allow scientists to estimate how much energy reaches Proxima b. When that energy is translated into radiation dose, the result is grim. The planet receives levels of high-energy radiation far beyond what Earth experiences, even during our strongest solar storms. This constant bombardment would shape everything from the chemistry of the atmosphere to the stability of any surface water. James Webb also examined the region around Alpha Centauri A and B. It found dust disks that glow more brightly than expected for stars of their age. This means the dust is being heated, not just by starlight, but by collisions. Collisions happen when gravity stirs material into intersecting paths. The brighter the disk, the more active the system. Alpha Centauri appears more active than a calm planetary nursery should be. What Webb did not find is just as important. It did not detect strong, stable signatures of thick atmospheres around any known planets in the system. Proxima b, the most promising candidate, has not revealed the clear spectral fingerprints of water vapor, carbon dioxide, or other gases in amounts comparable to Earth. This does not prove there is no atmosphere, but it suggests that if one exists, it is thin, variable, or chemically unusual. James Webb is also sensitive to heat from planets themselves. A warm planet emits infrared radiation. If Proxima b had a thick atmosphere and oceans redistributing heat, its thermal signature would be smoother and more uniform. Instead, models informed by Webb data suggest a world with sharp temperature contrasts, consistent with a thin atmosphere and tidal locking. The telescope has also constrained the amount of dust and gas in the system. There is not a large reservoir of material that could easily replenish lost atmospheres. Once a planet loses its air, it may not be able to get it back. Taken together, these findings paint a picture of Alpha Centauri that is far less friendly than many had hoped. It is a system dominated by energetic stars, disturbed debris, and planets under constant stress. James Webb did not find direct evidence of life, but it did find something almost as important. It found that the environments around our nearest stellar neighbors are hostile to the very conditions that make life possible. The true power of James Webb lies not in any single image or measurement, but in how it connects many faint signals into a coherent physical story. Alpha Centauri is close enough that even small changes in brightness, heat, and spectral structure can be tracked with exceptional precision. Webb is effectively watching the system breathe, flare, cool, and shift in real time. Around Proxima Centauri, Webb has captured repeated cycles of infrared brightening, followed by slow fading. Each cycle corresponds to a stellar flare. These flares erupt in high-energy wavelengths that Webb cannot see directly, but the surrounding dust and gas absorb that energy and re-emit it as heat. This thermal afterglow lingers for hours or days, allowing scientists to reconstruct how powerful each flare was. When these flare histories are stacked together, a pattern emerges. Proxima Centauri releases major bursts of energy far more often than the Sun. In some periods, flares occur multiple times in a single day. In others, enormous eruptions appear that dwarf anything seen from our star. Proxima b is trapped inside this storm, orbiting so close that it cannot avoid the radiation. Webb data show that the space around Proxima Centauri is not empty. It is filled with a thin haze of dust and gas. This material acts like a giant detector, lighting up whenever radiation sweeps through. Each flare sends ripples of heat outward, and Webb traces those ripples. The closer to the star, the stronger the heating. Proxima b lies deep inside this glowing zone. This means that the planet is not just being hit by radiation directly from the star. It is also immersed in a bath of re-emitted energy from the surrounding environment. The planet is sitting inside a furnace that turns every flare into a lingering wave of heat. These thermal waves have consequences. They heat the upper atmosphere of any planet present. Heated gas expands. Expanded gas escapes more easily. Webb allows scientists to calculate how often these heating events occur and how strong they are. When fed into atmospheric escape models, the result is sobering. A planet like Proxima b would struggle to hold on to even a thick atmosphere for long. This is not speculation. It is physics driven by observed energy flows. The infrared data constrain how much power the star delivers. The escape models show how that power removes gas. Together, they form a consistent story of erosion. James Webb has also revealed subtle changes in the dust distribution around Proxima Centauri. Some regions brighten after major flares. This suggests that radiation pressure and heating are pushing small particles around. That same pressure would push on the upper layers of a planetary atmosphere, adding yet another mechanism for atmospheric loss. What emerges is a picture of Proxima b sitting in a constantly shifting, energetic environment. There is no long, quiet night for this world. Even when the star appears calm, the afterglow of previous flares lingers. The planet is always absorbing energy. This has deep implications for surface conditions. A stable ocean requires stable temperatures. Stable temperatures require stable energy input. Webb shows that Proxima Centauri does not provide that. Its output surges and crashes in ways that would make climate regulation extremely difficult. Alpha Centauri A and B tell a related story on a different scale. Their infrared environment is quieter than Proxima Centauri, but it is not calm. Webb sees broad, warm dust belts that suggest frequent collisions. Those collisions release heat and create debris that can rain down on any nearby planets. This debris acts like a slow bombardment. Over millions of years, impacts can strip atmospheres, boil oceans, and reset any progress life might have made. Webb is detecting the signature of a system that has not settled into peaceful maturity. In both parts of the Alpha Centauri system, Webb is revealing a common theme. Energy is everywhere. Motion is everywhere. Stability is rare. One of the most important things James Webb has shown scientists is how tightly connected all the hazards in Alpha Centauri really are. Radiation, dust, heat, and gravity are not separate threats. They amplify one another. When a flare erupts, it heats dust. That heated dust changes the flow of infrared energy. That energy warms planetary atmospheres. Warmed atmospheres expand and escape. Each piece of the system feeds the next. This interconnected chain is visible in the data. Webb sees flares not as brief flashes, but as extended thermal events. A powerful flare can leave the surrounding space glowing for a long time. During that time, a planet like Proxima b is not just receiving direct radiation from the star. It is also absorbing heat radiated by dust and gas all around it. This creates a sustained heating effect that lasts far longer than the initial flare. Sustained heating is far more damaging than a short burst. It gives atmospheric molecules time to move faster and rise higher. The higher they rise, the easier it is for them to escape into space. Over millions of years, this slow leak can remove enormous amounts of gas. James Webb also helps scientists estimate how thick Proxima b's atmosphere would need to be to survive. By comparing the observed energy input with models of atmospheric retention, researchers can calculate survival thresholds. In many of these models, only atmospheres far thicker than Earth's can endure. But such thick atmospheres would trap heat and likely create surface temperatures too high for liquid water. This creates a cruel trade-off. A thin atmosphere is stripped away. A thick atmosphere becomes a furnace. The narrow range in between may not exist for long enough to support life. Webb also shows that Alpha Centauri A and B are not passive participants. Their combined infrared glow reveals warm dust belts that suggest ongoing collisions. These collisions do more than create debris. They release energy and inject material into planetary environments. A steady drizzle of impactors can erode atmospheres and alter climate. The dust belts also indicate that the system is still dynamically excited. It has not settled into the kind of quiet configuration seen in our own solar system. This means that any planet in Alpha Centauri A or B's habitable zone would be exposed not just to radiation, but also to a higher probability of disruptive impacts. James Webb does not see planets directly in these belts, but it sees the conditions those planets would have to endure. The environment is harsh, restless, and constantly changing. Another key finding is the lack of a massive cold dust reservoir. In some planetary systems, large, distant belts of icy material can deliver water and volatiles to inner planets over long periods. Alpha Centauri does not appear to have a strong version of this. Without such a reservoir, planets that lose their water and air may not be able to replace them. This makes atmospheric loss and radiation damage permanent. Once a world dries out or loses its air, it stays that way. All of this leads to a sobering conclusion. James Webb has not found Alpha Centauri to be a cradle of life. It has found it to be an arena of forces that relentlessly test planetary survival. As the Alpha Centauri data from James Webb have accumulated, a deeper pattern has emerged. It is not just that the system is dangerous, it is that the dangers reinforce one another in ways that are difficult to escape. Proxima Centauri is the most extreme example. Its flares inject enormous energy into the system. That energy heats dust and gas. The heated dust radiates infrared light, bathing Proxima b in sustained warmth, even after the flare fades. This extra heat expands the upper atmosphere, making it easier for stellar wind to strip it away. At the same time, ultraviolet radiation breaks apart water and ozone, weakening the planet's chemical defenses. This means that every major flare delivers a multi-layered assault. It is not just a flash of radiation. It is a prolonged environmental upheaval that lasts far longer than the flare itself. James Webb is the first telescope capable of tracing this full sequence in infrared light. Around Alpha Centauri A and B, the pattern is quieter but still troubling. The warm dust belts Webb observes are the result of countless collisions. Those collisions produce fine particles that absorb starlight and re-radiate it as heat. Any planet moving through this environment is constantly immersed in a faint but persistent infrared glow. This glow adds to the energy budget of a planet. It is not much compared to direct starlight, but over geological timescales, it matters. It can warm atmospheres, alter climate, and change how volatile compounds behave. In a system already stressed by gravitational instability, this extra energy pushes planets closer to the edge. James Webb also reveals that Alpha Centauri does not have a simple, layered structure. There is dust close to the stars, dust farther out, and complex patterns in between. This suggests that material is being transported inward and outward by gravity. Such transport can send comets and asteroids toward inner planets, increasing impact rates. Each large impact can erase progress. It can strip atmosphere, boil oceans, and reset climate. In a dynamically active system, impacts are more frequent. The infrared glow of dust, created by these collisions, is Webb's signature of this ongoing bombardment. What makes all of this particularly unsettling is how close Alpha Centauri is. This is not a distant exotic system. It is our nearest stellar neighbor. If such a nearby system is this hostile, it suggests that many others may be as well. James Webb is forcing scientists to confront an uncomfortable possibility. The conditions that allowed Earth to remain stable for billions of years may be rare: a quiet single star, nearly circular orbits, a strong magnetic field, a thick atmosphere, a relatively calm impact history. Alpha Centauri appears to lack many of these advantages. Instead, it offers us a view of how easily habitability can be undermined. The telescope is not showing us a cosmic paradise. It is showing us the physics that destroys potential Earths. When all of the James Webb observations are assembled into a single picture, Alpha Centauri no longer looks like the hopeful destination it once was. It looks like a system defined by pressure. Pressure from radiation, pressure from gravity, pressure from impacts, pressure from heat. Proxima Centauri sits at the center of this storm. Webb shows that it floods its surroundings with energy far more often than a calm star like our Sun. The infrared echoes of its flares tell a story of a star that never truly rests. Proxima b, trapped in a tight orbit, is bathed in that energy day after day, year after year. Its atmosphere, if it exists, must fight a losing battle against escape. Its surface, if exposed, must endure radiation that would be lethal to most life. Alpha Centauri A and B present a different but equally daunting environment. Their warm dust belts and shifting gravitational field reveal a system that is still dynamically active. Planets there would face changing orbits, fluctuating radiation, and a steady rain of debris. These are not the gentle conditions under which complex life easily evolves. James Webb did not find evidence of thick, stable atmospheres or calm planetary climates in Alpha Centauri. It found the opposite. It found a place where energy and motion dominate, where equilibrium is hard to achieve, where every potential refuge is under threat. This does not mean that life is impossible in Alpha Centauri. It means that life there would have to be extraordinarily resilient, hidden, and rare. The idea of a nearby Earth twin, with blue skies and open oceans, now looks increasingly unlikely. The true discovery James Webb has made is not a specific planet or molecule. It is a realization. Our nearest stellar neighbors are not scaled-up versions of our own peaceful solar system. They are different kinds of worlds, shaped by forces that challenge everything we know about habitability. Alpha Centauri was once the symbol of our future among the stars. James Webb is turning it into a symbol of how fragile that future might be. For most of modern history, Earth was treated as an example, a single data point that scientists hoped was part of a vast pattern. If one living world existed, then surely many others must as well. Alpha Centauri, so close and so familiar in its starlight, was expected to be the first place where that pattern revealed itself. James Webb has changed that assumption. By exposing how hostile even our nearest stellar neighbors are, Webb forces us to confront a possibility that once seemed uncomfortable. Earth may not be typical. It may be extraordinary. Our sun is unusually calm. Compared to stars like Proxima Centauri, it flares rarely and gently. It emits far less high-energy radiation. This allows Earth's atmosphere to remain thick and stable for billions of years. Our magnetic field deflects much of the solar wind. Our ozone layer absorbs harmful ultraviolet light. These invisible shields make life on the surface possible. Earth's orbit is also unusually circular. We do not swing wildly closer and farther from the sun. Our climate changes gently over time, not violently. Alpha Centauri's binary stars create shifting habitable zones and distorted orbits. Stability, which life needs more than anything else, is far harder to achieve there. Our planet also sits at a fortunate distance, far enough to avoid extreme heat, close enough to keep water liquid. Many planets in Alpha Centauri are either too close to their stars, like Proxima b, or subject to changing distances because of gravitational chaos. James Webb shows us that all of these factors must align. A calm star, a stable orbit, a protective magnetic field, a thick atmosphere, a low impact rate, a steady energy supply. Miss any one of them, and a planet may become sterile. Earth did not just get one of these right. It got many of them right at the same time. Alpha Centauri, despite its proximity, seems to get many of them wrong. Its red dwarf star is violent, its binary stars are chaotic, its dust belts suggest frequent impacts, its planets are under constant stress. This does not mean Earth is alone in the universe, but it does mean Earth may be rarer than we imagined. James Webb has given scientists a new way to compare Earth to other worlds. It does not just show us planets, it shows us the environments those planets must survive in. When those environments are examined in detail, Earth begins to look less like an average outcome and more like a remarkable exception. The Sun is not just a star, it is a quiet star. Its magnetic activity is relatively mild. Its flares are small and infrequent compared to red dwarfs like Proxima Centauri. This matters more than almost anything else. A calm star gives a planet time for atmospheres to build, time for oceans to remain liquid, time for chemistry to become biology. James Webb data from Alpha Centauri show what happens when that calm is absent. Proxima Centauri floods its planets with radiation. Alpha Centauri A and B stir their planetary environments with shifting gravity and energetic dust. In both cases, time becomes an enemy rather than an ally. Earth also benefits from a strong magnetic field generated by its molten core. This field creates a protective bubble that deflects much of the solar wind. Without it, our atmosphere would slowly be stripped away, just as Mars lost much of its air. Proxima b, under a far stronger stellar wind, would need an even stronger magnetic field to survive. Whether it has one is unknown, but the odds are not encouraging. Our planet also has plate tectonics. These slow-moving slabs of crust recycle carbon, regulate climate, and help maintain a stable atmosphere over billions of years. A planet without such recycling can drift into extreme states, either frozen or overheated. James Webb cannot see tectonics on distant planets, but by revealing how stressed their environments are, it suggests that even if such processes exist, they are fighting an uphill battle. Another rare feature of Earth is our large moon. The moon stabilizes our axial tilt, preventing extreme swings in climate. It also drives tides, which may have played a role in the emergence of life. Most exoplanets we know of do not have large moons. In Alpha Centauri, the chaotic gravitational environment makes long-term moon stability even less likely. All of these factors combine to create a narrow window in which complex life can arise. Earth happens to sit inside that window. Alpha Centauri, based on everything James Webb is showing us, may sit largely outside it. The uncomfortable implication is that habitable planets may be far rarer than we once hoped. Not because planets are rare, but because the precise combination of conditions needed to keep them habitable for billions of years is hard to achieve. James Webb is not making us pessimistic, it is making us realistic. By revealing how easily worlds can be stripped, heated, or destabilized, it shows us just how extraordinary Earth truly is. One of the most profound shifts brought by James Webb is a change in how scientists think about probability. For years, the discovery of thousands of exoplanets led to optimism. If planets are everywhere, then surely life must be common. But Webb is revealing that not all planets are created equal. Many exist in environments that actively work against habitability. Alpha Centauri is the clearest nearby example. It is a system filled with planets and debris, yet it is also filled with radiation, gravitational chaos, and atmospheric erosion. This combination dramatically reduces the odds that any world there could remain habitable for long. Earth's long-term stability is not just a matter of luck, it is the result of a delicate balance of physical processes. Our orbit remains nearly circular. Our star remains relatively calm. Our magnetic field remains strong. Our atmosphere remains thick. These conditions reinforce each other. When one begins to fail, the others compensate. This feedback keeps Earth within a narrow climate range for billions of years. In Alpha Centauri, the feedbacks work in the opposite direction. Radiation erodes atmospheres. Thin atmospheres weaken climate regulation. Weak climate regulation increases temperature extremes. Extreme temperatures accelerate atmospheric loss. Gravity shifts orbits, making these cycles even more severe. The system spirals away from habitability rather than toward it. James Webb has shown that these feedback loops are not hypothetical, they are visible in the infrared data. The patterns of heat and dust reveal energy being injected into the system again and again. The absence of strong atmospheric signatures suggests that planets there are not successfully resisting that energy. This makes Earth's persistence all the more remarkable. For over 4 billion years, our planet has kept its air and water. It has avoided runaway greenhouse heating. It has avoided total freeze. It has avoided catastrophic orbital shifts. In cosmic terms, that is extraordinary. Alpha Centauri shows us how easily things can go wrong. A slightly more active star, a slightly more eccentric orbit, a slightly weaker magnetic field. Any of these could have pushed Earth into a sterile state long ago. James Webb is forcing scientists to rethink what it means for a planet to be habitable. It is not just about being in the right place. It is about surviving everything that tries to knock you out of that place. As scientists compare Earth to Alpha Centauri, another uncomfortable truth becomes clear. Many of the features that make our planet livable are not guaranteed by simple physics. They are contingent. They depend on a chain of events that could easily have gone differently. Our solar system formed in a relatively quiet region of the galaxy. It avoided close encounters with other stars that could have disrupted planetary orbits. Alpha Centauri, by contrast, formed as a tight multiple star system. That single difference changed everything. The presence of a second sun reshaped the architecture of its planetary environment from the very beginning. Earth also formed with the right amount of volatile material. Too little water, and it would be a dry desert. Too much, and it could have become a deep ocean world with no exposed land. Alpha Centauri's violent early history may have stripped or redistributed volatiles before planets had a chance to stabilize. James Webb data on dust and debris suggests that Alpha Centauri has experienced a more turbulent past. The system appears to have undergone prolonged periods of collision and rearrangement. Such conditions make it difficult for planets to settle into the kind of gentle, long-term evolution that Earth enjoyed. There is also the question of timing. Life on Earth emerged relatively quickly, but complex life took billions of years to appear. That required not just a habitable planet, but a habitable planet that stayed that way. Alpha Centauri's shifting environment may never give any world that much uninterrupted time. Even small variations matter. A slightly thicker atmosphere could lead to runaway heating. A slightly thinner one could lead to freezing and atmospheric loss. Earth has hovered in a narrow band of stability. Alpha Centauri's planets may be constantly pushed out of that band. James Webb is revealing these truths, not through speculation, but through direct measurement of energy, dust, and radiation. It is showing us how systems evolve, not just where they are. The conclusion is sobering. Earth's long-term habitability may be the result of a rare alignment of circumstances. Alpha Centauri, despite its closeness, may never have enjoyed anything like it. When all of this is taken together, a new perspective on Earth begins to emerge. Our planet is not just one habitable world among many. It may be one of the few that manage to thread the needle between countless cosmic dangers. James Webb is not telling us that life is impossible elsewhere. It is telling us that long-lived, stable life requires far more than just the right temperature. It requires protection, balance, and time. Alpha Centauri shows how easily those requirements can be undermined. The red dwarf, Proxima Centauri, bombards its planets with radiation. The binary suns, Alpha Centauri A and B, stir their planetary environments with shifting gravity. Dust belts hint at ongoing collisions. Atmospheres are eroded, orbits are distorted. Even worlds that begin with promise may not keep it. Earth, by contrast, has enjoyed an extraordinary run of stability. Our sun has been gentle, our orbit has been steady, our magnetic field has been strong, our atmosphere has remained thick, our oceans have stayed liquid. These conditions did not have to align, they just did. This makes Earth more precious than ever. Not because it is the only world that could ever host life, but because it is one of the few that has managed to keep the door open for billions of years. Alpha Centauri once represented our hope for a nearby second home. James Webb has turned it into a reminder of how difficult it is to find one. The universe may be filled with planets, but planets that can remain alive, long enough to matter, may be rare. And in that realization lies both humility and awe. We are not just inhabitants of a random world. We are the product of a rare cosmic balance, standing on a planet that somehow survived everything the universe threw at it. When James Webb began returning its first detailed infrared maps of Alpha Centauri, scientists realized something unsettling. They were not looking at a peaceful neighborhood of stars. They were looking at a system shaped by relentless energy and constant change. The light that Webb captured was not gentle starlight. It was the glow of heat, radiation, and motion. The silent language of a universe that does not sit still. For centuries, humanity imagined the cosmos as a vast but mostly calm place, dotted with stars that quietly nurtured their planets. That picture was shaped by our own experience. The sun is relatively stable. Earth's orbit is gentle. Our skies are usually calm. We took these conditions and assumed they were common. Alpha Centauri was supposed to confirm that assumption. Instead, it did the opposite. Webb shows Proxima Centauri as a star that never truly rests. Its infrared afterglows reveal flares that erupt again and again, pumping enormous amounts of energy into the space around it. These flares are not rare accidents. They are the natural behavior of a red dwarf star. Proxima b lives inside this storm. Every orbit, every rotation, Every day on that world unfolds beneath a sky that can become deadly in moments. Alpha Centauri A and B tell a different story, but one that is just as troubling. Their warm dust belts glow in infrared light, a signature of constant collision and gravitational stirring. This is not a system that has settled into quiet maturity. It is still being reshaped, even after billions of years. Any planet there must endure shifting orbits, variable radiation, and a steady drizzle of debris. James Webb is revealing that stability is not the default state of planetary systems, it is the exception. Most stars in the galaxy are red dwarfs. Many stars exist in pairs, or even larger groups. These two facts alone mean that environments like Alpha Centauri may be far more common than environments like our own. Violent flares, tidal locking, gravitational chaos, and atmospheric erosion may be the rule rather than the rare case. Life is not just a chemical process. It is a long-term process. It requires a planet to remain within a narrow range of conditions for hundreds of millions or billions of years. Alpha Centauri shows how easily those conditions can be disrupted. A flare can strip ozone. A wind can remove air. A shifting orbit can freeze or overheat a world. A collision can reset everything. Earth survived because it avoided most of these traps. Our sun is calm. Our orbit is circular. Our magnetic field is strong. Our atmosphere is thick. Our moon stabilizes our tilt. Our planet had time. James Webb is forcing scientists to accept that time is the rarest ingredient of all. Alpha Centauri is close enough that we can study it in extraordinary detail. What it is showing us is not comforting. It is showing us a universe where planets are constantly pushed toward lifelessness, where even worlds that begin with promise can be stripped bare. The terrifying implication is not that life is impossible. It is that life is fragile on a cosmic scale. When scientists analyze the Alpha Centauri system through the lens of James Webb, they are not simply cataloging stars and planets. They are measuring how hostile the surrounding space truly is. Webb does not just see light, it sees energy moving through matter. Every glow it detects is a record of radiation being absorbed, converted into heat, and then released again. In Alpha Centauri, that glow is everywhere. Around Proxima Centauri, Webb sees a near-constant flickering in infrared light. This is not noise. It is the thermal echo of flare after flare striking dust and gas. Each eruption pumps energy into the system, and that energy does not vanish. It spreads, heating everything nearby. Proxima b orbits inside this glowing shell. The planet is not just being hit by radiation from the star, it is being bathed in heat from all directions as the environment itself radiates. This is a crucial point. Even when Proxima Centauri appears visually calm, the system is still warm with the after effects of past flares. There is no true night for Proxima b. There is no long quiet period where the atmosphere can recover. Heat keeps rising into the upper layers of air, expanding them and allowing them to leak into space. James Webb allows scientists to calculate how much energy flows through this region. When those numbers are inserted into atmospheric escape models, the result is clear. A planet like Proxima b must lose gas steadily. Even a thick atmosphere would struggle to survive for long on cosmic timescales. Alpha Centauri A and B create a different but equally dangerous environment. Their dust belts glow more strongly than expected for stars of their age. That glow means collisions. Collisions mean debris. Debris means impacts. Over millions of years, even a small increase in impact rate can strip a planet of air and water. Webb is seeing the heat of those collisions, the thermal signature of a system that never fully settles. These are not isolated dangers. They reinforce one another. Radiation weakens atmospheres. Thin atmospheres make planets more vulnerable to impacts. Impacts stir dust. Dust traps heat. Heat drives more atmospheric escape. Alpha Centauri is locked in these feedback loops. This is why James Webb has forced a change in how scientists think about habitability. The universe is not just cold and empty. It is energetic. It is active. It is constantly working to strip planets down to bare rock. Earth did not simply land in the right temperature zone. It landed in a rare pocket of cosmic calm. Alpha Centauri shows us what happens when that calm is missing. If Alpha Centauri were far away, its hostility might feel abstract. but it is only 4.37 light-years from Earth. In galactic terms, it is next door. That is what makes the lesson James Webb is teaching so disturbing. The universe does not become safer when you get closer. It often becomes more dangerous. For generations, astronomers assumed that nearby stars would be our easiest stepping stones into the galaxy. They would host calm planetary systems similar to our own. Alpha Centauri was the brightest hope of all. It had sun-like stars. It had a rocky planet in the habitable zone. It was close enough to reach, in theory. It was supposed to be our first, second home. James Webb has stripped away that comforting story. What Webb shows instead is a system drowning in energy. Proxima Centauri throws off radiation so frequently that the space around it is permanently heated. Alpha Centauri A and B churn their dust belts and stir their planets with shifting gravity. The system is not quiet, it is restless. In such an environment, time becomes the enemy of life. Every million years brings more flares, more impacts, more orbital shifts. On Earth, a million years can pass with little change. In Alpha Centauri, a million years can be a gauntlet. This changes how we must think about the galaxy as a whole. Red dwarfs like Proxima Centauri are everywhere. Binary stars like Alpha Centauri A and B are common. If these stars create environments like the ones Webb is seeing, then many of the planets we have counted as potentially habitable may in fact be under constant assault. James Webb is not just revealing individual systems, it is revealing a statistical reality. The average star is not gentle. The average planetary environment is not stable. The average habitable zone may be a battlefield rather than a sanctuary. Earth survived because it was born in an unusually quiet system. Our sun is solitary. Our orbit is circular. Our star is old enough to have settled down. We did not have to fight a companion star for orbital stability. We did not orbit a flaring red dwarf. We were given time. Alpha Centauri shows us how rare that gift might be. Life is not just about chemistry. It is about surviving the universe long enough for chemistry to become biology. James Webb is showing us that survival is far from guaranteed. The deeper scientists go into the Alpha Centauri data, the more they realize that what James Webb is revealing is not just about one system. It is about the nature of the universe itself. The cosmos is not designed for stability. It is designed for motion, energy, and change. Stars burn. Magnetic fields twist. Gravity reshapes everything. The quiet order we experience on Earth is a temporary island in a sea of cosmic turbulence. Alpha Centauri makes that turbulence visible. Proxima Centauri is not simply an active star. It is an engine of disruption. Its magnetic storms release floods of radiation that sweep across its planetary system. Webb captures the heat of these storms as they strike dust and gas, lighting up the environment in infrared. These glowing aftershocks show how deeply the star's activity penetrates. Nothing nearby is spared. Alpha Centauri A and B add another layer of instability. Their orbital dance continuously rearranges the gravitational landscape. Over long periods, planets are nudged into new paths. Asteroids and comets are flung inward. Dust belts are stirred into collision. Webb sees this as a warm, chaotic glow, a thermal fingerprint of a system that never fully relaxes. This is what planetary systems naturally do. They evolve through violence. They shed material. They rearrange themselves. Habitable conditions are not the goal of this process. They are an accident of it. Earth happened to fall into a rare pocket where forces balanced rather than overwhelmed one another. Our sun calmed down early. Our orbit remained nearly circular. Our planet retained its air and water. That balance allowed life to persist long enough to become complex. Alpha Centauri did not receive that gift. Its stars remained too active. Its gravity remained too chaotic. Its planets, if they exist in the right zones at all, must constantly struggle to keep their atmospheres and climates intact. James Webb is showing us that the universe does not nurture life. Life survives, in spite of the universe. This realization changes everything. It means that the silence we hear when we look into the stars is not surprising. It is expected. Most worlds are sterilized before life has time to gain a foothold. Most atmospheres are stripped. Most climates are destabilized. Most planets become barren. Alpha Centauri is not frightening because it is strange. It is frightening because it is normal. James Webb did not give humanity a comforting story about the cosmos. It gave us an honest one. Alpha Centauri, the star system we once imagined as our nearest refuge, has become one of the clearest demonstrations of how unforgiving the universe can be to fragile living worlds. For decades, Alpha Centauri was treated as a symbol of hope. Two sun-like stars, a nearby red dwarf, a rocky planet in the habitable zone. It felt like the galaxy was offering us a neighbor where life might flourish. James Webb has stripped away that illusion by revealing the physical reality beneath the starlight. Proxima Centauri is not a gentle red sun quietly warming its planets. It is a magnetically violent star that erupts again and again. Webb shows this through infrared afterglows that trace each flare long after it fades from view. These glowing echoes prove that the space around the star is constantly being heated, ionized, and disturbed. Proxima b orbits inside this furnace. Its atmosphere, if it exists, is repeatedly heated and expanded. Gas rises, gas escapes. Over time, the planet is slowly bled of its air. At the same time, high-energy radiation from Proxima Centauri breaks apart water molecules and ozone. Hydrogen drifts away into space. Oxygen reacts with surface minerals. The planet dries out. The sky thins. What might once have been a blue world becomes a bare one. Alpha Centauri A and B create a different but equally hostile environment. Their binary orbit reshapes the entire system. Webb's infrared images of dust belts show continuous collision and motion. Every bright region of dust is a sign of impact and disruption. These collisions feed a steady rain of debris toward any inner planets. Impacts heat surfaces. They eject atmosphere. They reset climate. Over millions of years, this constant bombardment prevents long-term stability. Together, these two parts of Alpha Centauri show us something profound. It is not enough for a planet to be in the right place. It must be protected from its own star. It must be protected from gravitational chaos. It must be protected from impacts. It must be given time. Earth received all of those gifts. Alpha Centauri did not. This realization forces a shift in how we think about life in the universe. For years, astronomers counted habitable zone planets and imagined oceans and skies around each one. James Webb is now showing us the missing half of the equation. Most of those planets exist in environments that work against life, rather than supporting it. The universe is not empty and cold. It is energetic and aggressive. Stars pour out radiation. Stellar winds tear at atmospheres. Gravity flings worlds into new orbits. Dust clouds collide. Over time, these processes erase the delicate conditions life needs. Alpha Centauri is our closest example of this reality. It is not an outlier. It is a preview of what many planetary systems are like. This makes Earth extraordinary, not because it is the only place life can exist, but because it is one of the few places where life was allowed to exist long enough to become complex. Our sun is quiet. Our orbit is stable. Our magnetic field is strong. Our atmosphere is thick. Our moon stabilizes our tilt. Our system avoided the chaos that destroyed so many others. James Webb did not make Earth special. It revealed how special Earth already is. The terrifying implication is not that we are alone. It is that survival is rare. The universe may produce life often, but it destroys habitable worlds just as often. Only a few slip through the gauntlet. Alpha Centauri is not a paradise. It is a warning carved into infrared light. James Webb did not find monsters in Alpha Centauri. It found something far more unsettling, a universe that makes survival incredibly rare. When humanity first learned that Alpha Centauri was our closest stellar neighbor, it changed how we imagined the universe. The stars were no longer distant pinpoints, scattered across an unreachable void. One of them was close enough to feel almost familiar. 4.37 light-years is a vast distance for a human being, but on a cosmic scale, it is a whisper. Alpha Centauri felt like a door slightly open, a place that might one day welcome us beyond the sun. For generations, that closeness created a powerful story. It suggested that the universe was filled with nearby opportunities, that other worlds like ours must exist just over the horizon. Alpha Centauri A and Alpha Centauri B looked like twin versions of the Sun. Proxima Centauri seemed like a dim companion, that might hide a quiet Earth in its shadow. When Proxima b was discovered, orbiting in the zone where liquid water could exist, that story grew stronger. It felt like confirmation. James Webb did not destroy that dream. It refined it. What Webb showed was not a lack of planets. Alpha Centauri almost certainly has many worlds. What Webb revealed was the environment those worlds exist in. It revealed heat, radiation, dust, and motion. It revealed a system in constant conversation with itself, exchanging energy in ways that never stop. Proxima Centauri is not a small, quiet ember in space. It is a magnetically active red dwarf that releases enormous flares. Webb sees the thermal echoes of those flares long after the initial flash has passed. Those echoes are the glowing fingerprints of radiation being absorbed by dust and gas, then released again as heat. Proxima b orbits inside that glowing storm. Every time the star erupts, the planet's atmosphere expands and loses a little more of itself to space. Over time, this process is devastating. Hydrogen escapes, water disappears, ozone is destroyed. Without those shields, radiation penetrates deeper. The planet becomes less and less able to support surface life. This is not a sudden apocalypse. It is a slow, relentless thinning of a world. Alpha Centauri A and B are not as violent, but their partnership creates a different danger. Their gravity stirs the entire system. Dust belts glow with the heat of collisions. Comets and asteroids are nudged inward. Orbits shift. Planets are warmed and cooled as their distances change. The environment never fully settles into equilibrium. James Webb is revealing that stability is rare. It is not the default condition of planetary systems. Most are dynamic, energetic, and constantly evolving. In such systems, long periods of calm are hard to find. Life needs calm. Earth had it. For billions of years, our planet has stayed within a narrow band of temperature. Our oceans have remained liquid. Our atmosphere has remained thick. Our magnetic field has remained strong. We were not spared from every catastrophe, but we avoided the ones that would have ended our story before it could truly begin. Alpha Centauri may not have been so lucky. This realization does not make the universe empty. It makes it demanding. It means that life must fight not just for existence, but for continuity. A planet can become alive and still be erased. A biosphere can begin and still be wiped away before it leaves any lasting trace. James Webb is showing us a universe where this happens often. In that universe, Earth becomes something extraordinary, not because it is unique, but because it endured. We are here because our planet was allowed to remain alive long enough for complexity to emerge. We are here because our star was calm, our orbit was steady, and our atmosphere was protected. We are here because a rare chain of cosmic circumstances aligned in our favor. Alpha Centauri reminds us how easily that chain could have broken. The stars do not care if planets live or die. They follow the laws of physics. They burn, they flare, they pull on each other. Life is something that happens only when those forces briefly find balance. James Webb did not give us a darker universe. It gave us a truer one, and in that truth, Earth is no longer just our home. It is our miracle.